In this example, we're starting with this epoxide and we're reacting it up under a couple of different sets of conditions. The first is just strict nucleophilic conditions, or you might see this referred to as sort of basic conditions. Okay, because OCH3- is a strong nucleophile and a strong base. In this second set of conditions, we're adding H+, so an acid, probably sulfuric acid, and then methanol. So this would be considered acidic conditions. And based on the conditions we're using, the products are going to change. So in the case of the basic conditions, OCH3 is a strong nucleophile, and the epoxide is a strained three-membered ring. And although O- really isn't normally a great leaving group, because of the ring strain, we can actually treat this with a nucleophile and open this epoxide up. So what happens under these basic conditions? We're going to do a nucleophilic attack on the epoxide. And let's just redraw this so we can kind of take a look at it here. Under strict nucleophilic conditions, the nucleophile is going to prefer to come in from the less substituted, or to the less substituted electrophilic carbon. So we have this electrophilic carbon and this electrophilic carbon. But this side of the epoxide is less substituted, so it's easier for the nucleophile to kind of squeeze in there and attack to open that epoxide up. So the product we get, when this opens up, we get our methyl still pointing up over here. Now this opening gives us an O-, and that's pointing back. And then since this is an SN2 type process, this OCH3 that comes in, it's coming in from opposite the side of our leaving group, which is this backward pointing epoxide, so the OCH3 is going to be pointing out. From here, now we just need to quench this reaction with a little bit of acid, some dilute acid. So we get an OH here pointing back and then pointing out. We get our OCH3. Now, switching to acidic conditions, we have a change. So our first step under acidic conditions is the nucleophilic lone pair on the epoxide gets protonated. So we can draw this intermediate with the proton attached. We still have our methyl here. Now, if we think about the electrophilicity of these two carbons, we need to think about which one has more partial positive character. So now that we have this positively charged epoxide, the mechanism changes. So in this example, we can kind of think of what would happen if this epoxide were to open up to form a carbocation. Well, here we would get a secondary carbocation, versus over here we would get a tertiary carbocation. So let's just think about that intermediate. we get this alcohol back, and then we can get a carbocation here. Now our HOCH3 can attack from the front side or the back side. So if we do attack from the front side, we get this product with the OCH3 and the H still attached, the positive charge, and then the methyl back, and then just a base from the solution can do a proton transfer. So we could get this product, and then we could also do nucleophilic attack from the back side at that carbocation. To give the methyl up and the OCH3 pointing backwards. But the big difference here to note is that our nucleophile, which was the HOCH3, under these acidic conditions, attacked the more substituted carbon. Whereas under the basic conditions, we attacked less substituted carbon to give this product.